Okay, let's have a look at the mass transfer, the mass balance of mass transfer to or from alpha mixed phase. So for example, there is mass transfer for alpha phase, which is in contact with beta phase. For example, for species J, and let be, we don't know that the J is reactant or product. So previously has been introduced to you that if mixed phase, you have to use this equation or mass balance. And this term of gain or loss to other phases simply means the mass transfer rate, right? The mass transfer rate. So contohnya yang ini ya. So species J, so you can include the volumetric alpha concentration of unreacted J at alpha phase. This is, for example, for J at mass transfer from alpha, which is in contact with beta. Okay, kemudian you kena tambahkan volume at alpha darab the summation of volumetric for all species times homogeneous reaction plus this is the rate of mass transfer. So the gain or loss, it depends whether the species is going to be appear or disappear. Okay, so here mass transfer rate of species J from phase beta to alpha, for example, kita darabkan the interfacial surface area darab this is the apa tu km saya tak ingat dah the mass transfer coefficient times concentration of J at beta minus concentration of J at alpha, which is this is the same as this formula in which J is something to do with the mass transfer coefficient or term. Okay. Okay, the mass transfer can be regarded as reversible surface reaction. So for example, area at alpha phase for species J, it's reversible for area for beta phase for species J. The pseudo-homogeneous rate. Pseudo-homogeneous rate means the overall rate or the one-dimensional rate. Okay, you tak masukkan, you tak masukkan kinetic reaction or mass transfer secara detail. Bukan you tak masukkan, you macam overallkan dia. Adalah bersama dengan in this equation in which that area divided by volume times R, the specific reaction rate. It's either mass transfer or kinetics, but in this slides or in this subtopic, we are talking about mass transfer rate. So ini adalah berkenaan dengan mass transfer reaction rate. Okay, kalau ia berkenaan dengan between phases, so area kita kena ambil the interfacial area which is alpha beta and divided of volume of alpha darab reaction specific tadi of mass transfer, in which that mass transfer rate is equals to this one. Okay, so ni tiba-tiba je dapat equation ni, so dia just nak cerita at steady state for mass transfer between phases. So this is the equation yang you akan guna. Okay, bermaksud concentration initial for certain reactant, in this case reactant A, minus the concentration of unreacted A, katalah at alpha phase, sama juga dengan tau space time at alpha phase times pseudo-homogeneous reaction rate plus which is tambah tau at alpha, lepas tu you darabkan dengan specific reaction rate pula. Okay. Okay, yang ini kita tengok pula mass transfer to or from unmixed phase. So sebagai contoh dekat PFTR, plug flow tubular reactor. So mass balance dia at steady state adalah sama dengan yang ini. Okay, average velocity at alpha times differentiation of concentration of species J at alpha phase divided by differentiation of Z of reactor or length of the fluid too. How long the fluid flows, how long the fluid travels. Okay. Sama juga dengan yang ini, summation of volumetric rate of different species times rate tambah mass transfer rate ni. Ini adalah pseudo homogeneous rate kan. So kalau untuk reactant A, contoh untuk reactant A. Okay, jangan confuse yang A yang ni. Yang ini adalah area. Yang ini adalah contoh untuk species A, reactant. Reactant tu kita namakan dia A. Katalah A tu adalah reactant. Yang ini kita tak tahu dia sama ada dia reactant ataupun product. So ini kita ambil contoh sebagai reactant. So you masukkan species A. Kemudian ni sebagai negatif. Okay, reaction rate dia sebagai negatif lah. Dan mass transfer rate dia pun kira kita panggil dia disappear, pun negatif. Okay, previous slide kita cakap unmixed phase. So kalau untuk mixed phase, ini adalah equationnya. You dah nampak sebelum ni kan? Ini bermakna cara nak kira concentration initial minus unreacted is also the same as this one for mixed phase. Untuk unmixed phase, untuk reactant A, so ini dia, which is dah cakap dekat previous slide juga. Okay, slide ni kita nak tengok theory of equilibrium constant. So, an equilibrium distribution of species A tadi between phases A and beta if the phases are in contact for really a long time. So, equilibrium constant kita boleh kira menggunakan teori yang ini, concentration of A at equilibrium at beta phase divided by concentration of A at equilibrium divided by alpha. Yang A ini jangan confuse, ini bukan reactant A. Ini adalah area dia. So kalau you nak kira mass transfer rate between phases, so maybe you boleh masukkan equilibrium constant kat sini. Sebab sebelum ni tak ada, katalah kita tak ambil kira equilibrium constant, bermakna rate of mass transfer dia adalah coefficient coefficient constant times concentration of A at beta minus concentration A at alpha. Tapi you kena masukkan equilibrium constant kat sini. Okay, ini kita panggil concentration gradient. Okay, concentration gradient in the vicinity of the interface, which is this is the driving force of the mass transfer. Okay, so ini adalah illustration dia lah, whereby, for example, this is the liquid phase and this is at gas phase. So kat sini adalah the concentration driving force dia, okay, at equilibrium. Okay, so kita tengok kat sini dia ada cakap if the equilibrium, if the driving force for mass transfer of a species disappears when the partial pressure of the species in the gas is in equilibrium with the concentration of the liquid phase. So kat sini kita dah guna theory of Henry's law, yang mana at constant temperature, amount of given gas that dissolves in a given type and volume of liquid is directly proportional to the partial pressure of that gas in equilibrium with that liquid. So this is the Henry's law theory. Partial pressure dia is equals to Henry's constant times the amount of the gas dissolved. Okay, and let's have a look at the example of gas liquid multiphase reactors. So contoh reactors of having contact between gas and liquid is falling film. Falling film ni tengok contoh reactant species A dalam gas phase, dia going through this one, this area. Kemudian species B, dia adalah dalam liquid, so dia going through this way. So ini kita panggil falling film. And then the bubble column, A dalam bentuk gas, it's bubbling up, and the B liquid, it's filling the column of this reactor, for example. And then catalytic wall film reactor, dia sama je dengan falling film, it's just that the wall is bertindak as the catalyst. Okay, trickle bed pula, A melalui yang ini, ya, dalam bentuk gas, and the B which is in liquid. Alright, dia beginilah keadaannya. Okay.